Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on amplifier. Okay, so for this video, I have some example to show it to you how can we actually design an amplifier or transistor so as to ensure that they actually remain stable using this way to calculate the gain, which is the maximum available gain. So basically, this video objective is to ensure that how you can actually successfully design amplifier or transistor and to ensure that it remains stable, what will be the maximum available gain that you can achieve from this design. This will be the part 15 series discussion on amplifier. So guys, if you're keen to know more about amplifier, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on amplifier. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, if you want to have a faster response, I strongly urge you to ask your question through the comment. Before I continue, I'd like to urge you guys to help this channel by pressing the like button. When more you guys actually help to press the like button, this video will have a better chances to reach out to a larger audience. So guys, help me press the like button now. For those who are new to this channel, please consider to subscribe to this channel and turn on your notification bell. Once again, thank you so much for strong support. Let's quickly take a look on the question. So there are altogether 3 questions. To show it to you, how can you actually design amplifier and also transistor so as to ensure that they remain stable? Coming to the first question here, a student actually record a set of S parameters measurement on a BJT transistor at a frequency of 100 megahertz, and the biasing condition is shown over here. VCE equals to 10 volt, while the current at the collector equals to 10 milliampere. Explain whether there will be a change to the set of S parameters reading when the frequency change. When we actually change the frequency, earlier on it is actually 100 megahertz. So when we actually change the frequency from 100 megahertz to 150 megahertz, will there be any change of S parameters while we remain the biasing condition the same, which is shown over here? So what will happen if we only purely just change the frequency? You can see that the S parameters in fact will change. Because if you know that S parameters, the values is actually depend on frequency. So hence when frequency actually change from 100 megahertz to 150 megahertz, the S parameters will be changed. Why I explain this? This means that, for example, when you actually calculate that 100 megahertz, it is actually so-called stable. When you change to 150 megahertz, you still need to recalculate whether the transistor will be stable or not. Because as you see from here, the S parameters will change, and hence, to determine whether it will be stable, you need to do it again, because once S parameter change, the stability Rayleigh factor K may also change. So hence, we need to double confirm whether the transistor will be able to remain stable or not. So basically, this is why I share this with you. Next, the biasing condition actually changed. As you can see over here, the VCE is equals to 5 volt. It was 10 volt, so now it reduced to 5 volt. While the current at the collector, they also reduced to 5 milliampere. So now, whether there will be any change of the S parameters while we keep the frequency the same at 100 megahertz. Again, I actually explained this at the part 14 series discussion. When we actually change the biasing condition, basically, the stability condition you need to recheck again. So basically, also, this actually bring out another use case here. For example, when I actually have this design, this design is not able to remain stable, then one thing I can do is I can actually alter so-called the biasing condition. As you can see from here, when I actually alter the biasing condition, again the S parameter will change, and the K, which is the Rayleigh stability factor, it may also change. So in short, for example, when you change the frequency, okay, because of the change of S parameters, you need to recheck. While over here, you show that, for example, for this case here, okay, so if the transistor remain unstable, I can actually always change the biasing condition, and I can have the possibility that the stable transistor may be able to work now. The second question here, okay, the stability circle of 4 different transistors are shown below. Okay, so also on the next few slides, okay, shape the area that is correspond to the stable region. Okay, so the shaded part will be the stable region, and then you indicate on the figure, okay, whether the transistors are unconditioned stable or condition stable. Okay, let's take a look on this here. So this is actually the so-called another circle here. It can be either the input or output. One thing I want to highlight here is the center point of the Smith chart will be always stable. So from here, you can actually see that this part in red, they are actually stable. For this part, so-called that is not shaded, this part is so-called the unstable zone here. So basically, this is to answer the first question. The shaded in red, they are actually stable. Okay, so basically from here, you can see that you need have additional condition in order to remain stable. Okay, I could not afford them to fall into this area. So basically the condition to remain stable is they must not fall in this region. So as long as they are not in this region, they will be remain stable. Okay, so basically this is the first case, okay, how to see the stability circle. Okay, next case here. Okay, as I highlight here, okay, so the center point will be always stable. So from here, you can see that the whole Smith chart so-called is so-called shaded, which means that any point in the Smith chart you use, they will be stable. So from here, you can see that this condition, we call this unconditioned stable. Okay, because regardless of any use case here, okay, the transistor will be always stable. So therefore, we call this as unconditioned stable. Third case here. Okay, so third case is basically slightly different here. Okay, so basically you can see that this part here can be input, can be output reflection coefficient again. Okay, at the center of the Smith chart, they are always stable. So therefore, from here you can see that this part is always stable. So basically, this is what I mean here. So for this case here, because okay, I need to have certain so-called condition here, you can see that this part they are actually so-called unstable. Okay, so therefore, okay, I need to so-called declare that this transistor as a conditionally stable because I need to ensure that they are not within this point here. Okay, so basically because of this, so therefore the transistor I can only declare them as conditionally stable. Okay, so basically this is the third one. Let's come to the last one. Okay, so basically you can see that this circle cover the whole thing. Again, the center is always stable. And based on this case here, again, you can imagine that this is what we call the unconditioned stable, which means that the transistor will be always stable because you can see that the whole of the Smith chart, they are actually shaded. Okay, next. Okay, again, guys, before I continue on the third example, I'd like to urge you guys to help this channel. If you have learned something from this channel, urge you to like this video and subscribe to this channel. Once again, thank you so much for strong support. Let's come to the third question here. Okay, so an RF transistor, they basically have the following S parameter at a given bias condition at 300 megahertz. So you can see from here, okay, basically they give us the bias condition and also the condition, okay, the frequency at 300 megahertz, and these are the set of S parameters. The RF transistor is used to design a 15 dB gain amplifier. Okay, so basically the achievement is to ensure at least 15 dB gain, okay, at 300 megahertz. The amplifier is to operate between 50 ohm termination. Okay, firstly, okay, so we need to determine whether the transistor is stable or not. So we need to calculate the stability factor. So once we calculate the stability factor, okay, we will be able to determine whether the transistor will be stable or not stable. Next, the question will also task us to calculate what is the maximum possible available gain, okay, which means that what will be the highest possible gain that this transistor can achieve. Once we calculate that number and we actually compare against the objective of the gain of 15 dB, then we will be able to know whether this transistor can be used, okay, to achieve a total of 15 dB gain. Let's come to this question. Okay, so firstly, okay, we need to verify the stability of the transistor. Okay, so we need to calculate the Rolex stability factor K here. Okay, so this is the equation to calculate. Okay, so basically from here, okay, so this is on on my part 14, I actually took this as a delta. Okay, so basically I have the S11 parameter, S22 parameters, S12 and S21 from my previous page here. So when you actually buy the transistor, they actually have this so-called data sheet. Okay, so after that, I actually can calculate this ds or delta here. Okay, in terms of mathematics, I will not be able to say so much, but over here you can see that I actually multiply these two things together first, and then I multiply these two things. I combine them into here. Then after that, I actually obtain the so-called equation here. Okay, so basically I just need the magnitude. Okay, so therefore this so-called delta is actually equals to 0.159. Okay, so again, I'm not able to show clearly all the mathematical calculation here. Because in fact, nowadays, it will be much easier to punch your calculator to get all this answer. Okay, in my day, it probably a little bit challenge. Okay, nowadays, okay, you can do easily to punch all this answer in a calculator form. Okay, and you just need to extract the magnitude, okay, which is 0.159 over here. Okay, so with this, we are ready to calculate the Rolex stability point. Okay, so again, these are the formula. Okay, so this ds I calculate earlier on, which is 0.159. I actually calculate, and basically I have this value here. So basically, since k is equals to 1.304, okay, which is more than 1, okay, which means that the transistor is unconditionally stable. Okay, so basically they will remain stable. So basically, let's finish this task here. Okay, so now we need to calculate the maximum available gain. Okay, remember it is actually tasked to have a gain of 15 dB. Whether they will be able to achieve, whether they are not able to achieve. Let's do a calculation here. Okay, so if you still remember, okay, we need to calculate the B1 value. Okay, so we need to calculate the B1 value. If B1 value is more than, in fact, you just whether is it positive or negative. For this case here, this is positive, which is mean that it's actually more than 0. Okay, over here you can see that it's a minus. If this calculation of B1 is negative number, then this part here will become a plus. Okay, so if you are not so sure about this, you can always take a look on my previous discussion, part 14, to understand this better. Okay, but over here, let's quickly do this again. So basically, we need to determine the B1 value. So basically, once we achieve the B1 value, we want to see whether is it so-called positive or negative. And then basically, this unit will be changed. For this case, this is positive, then this will be negative. If this is negative, then this will be positive. And from here, you can compute that this maximum available gain is 19.25 dB. If you still recall, the question actually asks whether this transistor can achieve the gain of 50 dB. From here, it is quite clear that this transistor will be able, okay, to provide a gain of 15 dB. Okay, so with this, I like to end my discussion. But over here, you can see that I have successfully designed, okay, a transistor or an amplifier, okay, using Rolex stability factor first, okay, to determine, okay, whether the amplifier or transistor will they be able to remain stable. So after that, I actually so-called calculate that this transistor is actually stable. So then after that, okay, I actually calculate the maximum available gain. So from this value here, you can see that this amplifier or transistor, they can be easily achieved of a gain of 15 dB, since the compute one of the maximum available gain, okay, which is 19.25, which is bigger than 15 dB. With this, I'd like to end my discussion. Okay, again, like to urge you guys to help this channel by like the video. Okay, so once again, thank you so much. I hope to see you guys soon. Bye for now. Thank you.